We will be discussing the problem in Pitel's book at page 102, number 3.4. The four forces shown act of the rollers of an inline skate. Determine the equivalent force couple system, with the force acting that O. Let us first identify the required in this problem. First, let us solve for the resultant force in the diagram. Since the forces are all directed at the y-axis, we can just add them all up to get the resultant, which is 154 pounds. Now, let us proceed in solving the moment at point O. Since our moment center is point O, we have to multiply the corresponding forces with its distance from point O, giving us this answer. We will be discussing the problem in Pitel's book at page 104, number 3.12. Do cable tensions and couple act on the rod OAB? Determine the equivalent force couple system with the force acting that O. First, we need to identify what are given and what's required in the problem. In the problem, we are asked to find the force and couple that can replace the two given forces and couple. First, let us convert the forces in its vector form. To find the resultant force, we need to add the two forces in its vector form. After doing so, we will be able to get this answer. Now that we already have the resultant force that will be placed at point O, the only thing left to do is to find the couple that will come along with the force. To find the couple, we need to multiply the force R to the distance of the initial point of application 2.0, or we can use the two forces earlier and multiply it with the distance of the original point of application 2.0 to find the couple. In this video, I chose to multiply force R with the distance of point O from the original position, which is 4 joules. If you were to choose the two forces, you'll be needing to find the cross product of 4 joules and one of the forces, then repeat it using the other force. Then at the two moment that we can get to find the required couple. The force product that we will be able to solve is the couple that we need. We will be discussing the problem in Pitel's book at page 115, number 3.24. Determine the resultant of the three forces and the couple C, and show it on a sketch of the coordinate system if AC equals 0, BC equals 90 Newton meter. First, let us identify the given and the required. Let us go to letter A. Since we are only asked for the resultant and the point of application, we can start this by finding the resultant of the forces using the force equation. Now that we know the resultant of the forces, which is negative 60I, we are now to find its point of application. We must first find the moment center. I am going to use point O as a moment center. Now let us establish the moment equation. If the sum of the moments will be 0, then the resultant will lie in this point. If not, we have to solve for its point of application. Since the sum of all moment is 0, then the point of application is point O. Now, let us proceed with letter B. Since the forces did not change, we can use the resultant of the force at letter A and letter B, and the couple C now has a value of 19 Newton-meter. So we cannot use point O as the point of application of the resultant, for the summation of the moments will not be equal to 0. In order to find the point of application of the resultant, we need to establish the moment equation with an unknown variable. Since, if we are to use a change in the x-axis, we will be having a problem, because the forces at the y-axis cancels out. We can only change the location of the resultant at the y-axis. With that assumption, we will be able to get this equation and solve for its new location at the y-axis, which is 1.5 meter above point O. We will be discussing the problem in Pitel's book at page 125, number 3.32. Determine the resultant of the three cable tensions that act on the horizontal boom if T sub 1 is equal to 900 pounds. T sub 2 is equal to 500 pounds. And T sub 3 is equal to 300 pounds. First, let us identify the given and the required in the problem. Then, let us transform the three forces in its vector form. To find its resultant, we need to add all of the three forces to be able to solve for the resultant force. The point of application of the resultant force will be the same as the original point of application of the three forces. Since none of them had a different point of application, we will be discussing the problem in Pitel's book at page 126, number 3.37. Find the resultant of the three forces acting on the square plate. First, let us identify the given and the required in the problem. Then, let us solve for the resultant force, since it is faster to solve than the point of application. After that, find the respective moment of the forces in any point in the figure. In this video we use the origin as the moment center for all calculations. After getting all of the moment, add them all to solve for the resultant moment. We can use the resultant moment to find the point of application of the resultant force. Since we already know the resultant force and the resultant moment, we now use the equation that we know to solve for its point of application. The equation that we are going to use in this problem is the cross product of the force and the distance, which is the moment. Since we are given with the force and the moment, we only need to know the distance. To find the distance, first, we write the distance r as xi plus yj, since The point of application of the force can only be present at x and y axis, for all of the forces are located only on the x and y axis. Next is to get the cross product of the force r and the distance r that we established to solve for its point of application, and we equate it to the resultant moment we earlier had. Then, we will now be able to solve for the distance of the resultant force in respect with the x and the y axis, in which it lies in the coordinate 3x, 3y, and 0z. We will be discussing the problem in Pitel's book at page 136, number 3.48. Determine the resultant of the line load acting on the beam ABC. First, let's identify the given and the unknowns. Then, we should change the distributed load into individual forces. Let's start with the distributed load at AB. We first start into a single force with a magnitude that is equal to the area of the distributed load, AB. Then we locate that single force 1/3 away from the side with a 90-degree angle, which is 4 feet from point A. Now, let's transform the distributed load at BC. In order to change it, we first separate it into two different parts. The first part is a rectangle having a side at the x-axis of 8 feet, and the side at the y-axis of 1,200 pound/foot. While the second part is a right triangle with a longer leg of 8 pound/foot, while the shorter leg of 500 pound/foot. We now start transforming the distributed load. We begin with the rectangular one. We first transformed it into a single load by getting the area of the rectangular distributed load. Then, we position the force at the middle of the length of the distributed load. Then, let's do the triangular part. We do the same procedure that we have done at the distributed load at AB. Now that we are able to transform the distributed load into 3 individual forces, now let's find the resultant force of the system. We must add all up the forces to solve for the resultant force. We then find the point of application of the resultant force. First, we assume the moment center in this video. Point A is the moment center used. Point B and C can also be used as a moment center, and they should yield the same answer. Next, we are to establish the moment equation in respect with the desired point to solve for the resultant moment. Now we know the resultant moment and the resultant force. We can now locate the position of the resultant force. We just equate the product of the resultant force and x, where x is the distance of the resultant force from force A, and the resultant moment. After solving this equation, we could solve the distance of x, which is 8.75 feet. We will be discussing the problem in Pitel's book at page 137, number 3.52. At a certain time during a hurricane, the wind pressure acting on the wall of a high-rise building varies linearly as shown. Determine the resultant force caused by the wind. Let us first identify the required in this problem. Since we are given the distributed load at this figure, then we would be needing to take account the area of application in the system. We can see that the area affected by the distributed load changes at an altitude of 180 feet. So, we will have to divide this system into two different systems, which consists of two different rectangular prisms. Now, let us evaluate the distributed load on our larger prism. As we can see, we don't know the value of the distributed load at the 180 feet altitude. We will have to establish a relationship for the distributed load. First, let us separate the rectangular component of the distributed load from the triangular component. Then, let us analyze the triangular component of the distributed load. As we can see, our unknown and the 3.2 pound per foot squared will be located at the shorter leg, while the altitude will be located at the longer leg. Since we need the value of the unknown in the shorter leg, we can use a trigonometric function that utilizes the two legs of the right triangle to solve for the angle. We can either use tangent or cotangent to solve for the unknown. Doing so, we will get the unknown as 0.84 pound per foot squared. Now, we already know all of the present load in the distributed load. We can now replace the distributed load with a concentrated force. Since it is not rectangular or triangular, we are to divide it into pieces. After dividing it into pieces, we will be able to make a two-piece which is rectangular and triangular. Since it is in 3D, we are to analyze it into axes. First, let us analyze the triangular part. In this shape, when making it into a singular force, we are to place the singular force in the middle of the x-axis, and 2/3 of the height in this problem since the distributed load is vertical. Next, we evaluate the rectangular part. In this shape, we always locate the singular force in the middle of the area of application of the distributed load. Now, we already know where it is located. Let us then compute for the amount of force present in those forces. In order to get the force in the system, we are to find the area of the shape, like so. Now, let us do what we have done with the larger rectangular prism with the smaller. After doing so, we will find this answer. Now that we know all of the forces that acts on the system, we can now solve for the resultant force, which will be equal to the summation of all the forces. After that, let us get the moment of each force with respect to any point. In this video, we will be using the origin as the moment center. Before we can solve for the moment, we must first identify the distance of the moment center from the forces in vector form. After we get them, let us get the cross product of the force and the distance that we were able to get, like so. This is just the continuation in solving for the moment. Now, we already have the value of the moment of each of the forces at point O in the definition of moment and forces, that the resultant moment is equal to the cross product of the distance and the resultant force, and it is also equal to the summation of all the moment of each force in the system. Since we already know the moment of all forces, we now need to identify the equation of the resultant moment, so we could get from the cross product of the distance and the resultant force. We will get that equation by multiplying the solved resultant force with the unknown distance that we could name as xi plus yj plus zk. The cross product will yield to this equation. Now let us equate the equation that we were able to derive with the summation of all the forces in the system, which will give us to the point of action of the resultant of the forces caused by the distributed load of the wind, which is X is equal to 59.1 feet, Y is equal to 0, and Z is equal to 135.6 feet.